So today's lecture is about continuous functions on closed intervals. What makes Calculus 1 work? And that's just a little bit of an overstatement, but not too much. Start off with continuous functions on closed bounded intervals are themselves bounded. So suppose that we have f, a function from the closed interval a, b to the real numbers r is continuous. Then there is a number m such that negative m is less than or equal to f of x is less than or equal to capital M for all x element of the closed interval a, b. Okay. To prove this, we will proceed by contradiction. And to get a contradiction, suppose that for every m, there is an x element of AB such that the absolute value of f of x is greater than m. It follows then that for every n element of the natural numbers, there's an x sub n element of AB such that f of x is greater than n. Okay, f of x sub n is greater than n. So by the Bolzano-Weierstrass theorem, there is a subsequence of xn that converges to some point c element of the closed interval AB. And to save notation, let's just assume that the original series xn itself converges. This just saves us some writing. Since f is continuous, f of xn converges to f of c. However, this is contradicted by our choice that the absolute value of f of xn is greater than or equal to n for every n. Therefore, since we have a contradiction, f of xn must be bounded. Okay, continuous functions on closed bounded intervals achieve their extrema. So in the previous theorem, we proved that the function is bounded. Now we're going to prove that our continuous function will achieve their extreme points. Okay, so suppose that f from the closed interval a, b to r is continuous. Then there are L and M elements of the closed interval a, b such that for all x in the interval from closed interval from a to b, that f of m is less than or equal to f of x is less than or equal to f of L. So before, when we prove it's bounded above and below, we know that there's a least upper bound and a greatest lower bound for the image of f. Here we're proving that we actually achieve those bounds. And so let's let L be the least upper bound of f of AB. Okay. For every n element of natural numbers n, there is an x sub n element of the closed interval AB such that L minus 1 over n is less than f of x sub n is less than or equal to L. So we get, this is our trick thing, that we can always squeeze a member of the set between the least upper bound and something that's just a little bit smaller than the least upper bound. And so of course the sequence of f of xn converges to L. Okay. Now by applying the Bolzano-Weierstrass theorem, there's a subsequence of our original sequence xn that converges to some number little l. To save notation, assume that xn converges to L. Okay. Since f is continuous, f of xn then converges to f of L. But we already knew that f of xn already converged to L, so f of L must be equal to capital L. And so it now follows that f of x is less than or equal to f of little l for every x element of AB. And we can do something similar now for the lower bound. Okay. All right. The last thing we're going to do today is prove the intermediate value theorem. Suppose that f from a to the closed interval a, b, into the real numbers is a continuous function. Suppose that x1 and x2 are elements of the closed interval a, b, such that f of x1 is less than f of x2. If n is between f of x1 and f of x2, there is a c that is between x1 and x2, such that f of c is equal to n. So roughly, this is saying that when you draw your graph of your continuous function, you don't pick up your pencil. Okay. So now, given n, okay, between f of x1 and x2, we will find that c between x1 and x2 such that f of c is equal to n. Let I sub 1 be a closed interval with the endpoints x1 and x2. And notice I'm kind of writing this in general. We don't know that x1 is less than x2. Okay. Now, note that f maps one endpoint of x1 above n and one point of x1 below n. Label the endpoint that of the I sub 1 that f maps above n as u sub 1. We'll call it upper. The other endpoint that will be mapped below n, we call it d1. We call it for down. So u is for up, d is for down. Now let m be the midpoint of that interval I1. Okay, if f of m of 1 is equal to n, then we're done. Okay, but that's not going to happen except in very special cases. Okay. Otherwise, what we will usually do is we'll have either f of m1 will be bigger than n, or f of m1 will be smaller than m. It follows that there is an interval I2 that is half of the interval I1 split at m1 that maps one of its endpoints above n and the other below. Label these as u2 and d2, up to and down to respectively. Okay, so we continue in this way. Okay, constructing a sequence of intervals that are nested within each other, such that in has an endpoint un that is mapped above capital N, and an endpoint that is dn that is mapped below capital N. By the familiar argument, there is a unique c that is common to all of the intervals in. We claim that f of c is equal to n. Note that both un and dn converge to c, so that f of un and f of dn converge to c by continuity. Therefore, we have f of c is greater than or equal to n is greater than or equal to c. So, hey, everything's equal to c. And we're done.